Welcome, my dear listeners. Today we embark on a journey into the heart of darkness itself, into the lives of black holes. They are born in the fiery deaths of stars. They grow by devouring matter. They merge and shake the very fabric of space-time, and in the end, they evaporate into nothingness. But as we shall see, black holes are not merely destructive. They are also creators, shapers of galaxies, laboratories of physics, and metaphors for the limits of human knowledge. Let us begin where black holes themselves begin, in the life and death of massive stars. A star is a delicate balance, gravity pulling inward and nuclear fusion pushing outward. For millions or billions of years, that balance holds. In the heart of the star, hydrogen fuses into helium, then helium into heavier elements, releasing the energy that makes stars shine. But eventually, even the mightiest stars run out of fuel. When that day comes, gravity wins. The core of the star collapses, and the outer layers explode outward in a supernova. What remains is an object so dense, so compact, that nothing, not even light, can escape its grasp. This is the birth of a stellar black hole. Imagine this: a star 20 or 30 times more massive than our Sun, compressed into a sphere only a few kilometers wide. A teaspoon of its matter would weigh billions of tons. It is the triumph of gravity, taken to the extreme. And yet, despite their terrifying density, stellar black holes are invisible in themselves. We can only find them through their effects, the way they tug on nearby stars, or the way they light up the sky when they feed. One famous example is Cygnus X-1, the first widely accepted black hole candidate discovered in the 1960s. It is part of a binary system, a blue supergiant star orbiting an unseen companion. That invisible partner pulls matter from the star, creating an accretion disk that glows in X-rays. For decades, Cygnus X-1 was the battleground of theory and skepticism. Stephen Hawking himself once bet against its being a black hole, and later conceded the bet. Stellar black holes remind us of the cycle of life and death in the universe. Just as a tree falls and becomes the soil for new growth, the death of a star in a supernova spreads heavy elements, carbon, oxygen, iron, into space. Those elements become the building blocks of planets, of oceans, of life. And in the middle of that cosmic recycling, sometimes, a black hole is born. Philosophically, stellar black holes force us to confront the paradox of endings and beginnings. Is the collapse of a star the end of its story, or the start of a deeper mystery? For the star itself, it is death. But for the cosmos, it is a transformation. Matter and energy change form, and what seems like destruction becomes creation. Scientists like Subramanian Chandrasekhar, who calculated the limits of stellar collapse, and John Wheeler, who coined the term black hole, gave us the language and the framework to describe these objects. Their intellectual courage reminds us that science is not just about equations, it is about daring to imagine the unimaginable. So, stellar black holes mark the beginning of our journey. They are the seeds of the black hole family. Some of them will merge, grow, and perhaps one day become the supermassive giants at the centers of galaxies. Others will drift silently through space, invisible, undetected, yet still warping the fabric of the cosmos with their gravity. And as we contemplate their existence, we must ask ourselves, if such extremes exist in nature, what else might the universe hold? If gravity can collapse a star into an object smaller than a city, what does that say about the power of the laws that govern reality? And most importantly, what does it say about us, that we can understand them at all? If stellar black holes are the seeds, then supermassive black holes are the towering trees of the cosmic forest. These giants, millions to billions of times more massive than the Sun, sit in the centers of nearly every large galaxy. Invisible in themselves, they reveal their presence through their immense gravitational pull and their dramatic effects on their surroundings. Our own Milky Way is no exception. At its heart lies Sagittarius, a star, a supermassive black hole with about 4 million solar masses. How do we know it is there? Because we can watch stars whipping around an invisible center at breakneck speeds. Andrea Ghez and Reinhard Genzel spent decades tracking these stars, their patience rewarded with a Nobel Prize in 2020. Their observations gave us the clearest evidence yet of a supermassive black hole lurking in our galactic core. But a mystery remains. How did these giants form? Did they start as stellar black holes that slowly grew, feeding on gas and stars, merging with their kin until they reached monstrous proportions? Or did they form directly, collapsing from enormous clouds of primordial gas in the early universe? Some even suggest they were born mere hundreds of millions of years after the Big Bang, a timescale so short that their existence challenges our theories. Supermassive black holes are not passive. When gas spirals into them, it can form blazing accretion disks, heating to such extremes that they outshine entire galaxies. These are quasars, beacons visible across billions of light years. Some of the quasars we see today shone when the universe was less than a tenth of its current age. Looking at them is like peering into cosmic prehistory. Then there are the jets, immense streams of plasma launched from the regions around black holes, shooting out at nearly the speed of light. The galaxy M87 hosts one of the most famous. In 2019, the Event Horizon Telescope collaboration stunned the world by unveiling the first image of a black hole's shadow, the dark silhouette of M87's supermassive black hole against the glowing ring of its accretion disk. Alongside it stretched the galaxy's colossal jet, a structure so vast it dwarfs entire star systems. Philosophically, supermassive black holes invite us to think on scales almost beyond imagination. 1 billion suns, compressed into a region smaller than our solar system. What does that mean for our place in the cosmos? They remind us of both our smallness and our greatness. Small, because we are tiny creatures in a galaxy governed by such power. Great, because we can measure, model, and even photograph these incomprehensible entities. They also raise profound scientific questions. Which came first, the galaxies or the black holes at their centers? Did galaxies form around black holes, drawn in by their gravity? Or did the black holes grow inside galaxies that already existed? If the former, then black holes are not just cosmic parasites, but architects of structure in the universe. The story of supermassive black holes is also a human story. For decades, astronomers debated whether quasars were local oddities or truly distant, unimaginably bright objects. The latter turned out to be true, and with that realization, our conception of black holes shifted from theoretical curiosities to central players in cosmic evolution. Scientists like Martin Schmidt, who first identified quasars, or Shep Doeleman, who led the Event Horizon Telescope project, embody the determination to uncover the invisible. So, supermassive black holes are not just endpoints of stellar collapse. They are engines of galaxies, beacons across the universe, and challenges to our understanding of cosmic history. They force us to ask, if such colossal entities exist at the heart of almost every galaxy, what role do they play in shaping the story of the universe itself? Between the stellar black holes born from dying stars and the monstrous supermassive black holes in galactic centers, there ought to exist something in between. For decades, astronomers have searched for these elusive middleweights, intermediate mass black holes, ranging from a few hundred to a few 100,000 solar masses. They are the missing link in our cosmic bestiary. The logic of their existence seems irresistible. If small black holes can grow into supermassive ones, surely there must be intermediate stages. Otherwise, how did the giants form so quickly in the early universe? Yet, for a long time, these objects remained hypothetical, invisible phantoms in our theories. The problem is one of detection. Stellar black holes reveal themselves in X-ray binaries, feeding on companion stars. Supermassive black holes blaze as quasars. But intermediate black holes are trickier. Too massive to form typical X-ray binaries, too small to light up like quasars, they seem to hide in the shadows. And yet, clues have emerged. In dense star clusters, the motions of stars suggest the pull of something heavier than a typical star, but lighter than a supermassive black hole. One candidate is found in the Omega Centauri cluster. Other hints come from ultra-luminous X-ray sources, objects whose brightness suggests accretion onto black holes larger than stellar mass. The real breakthrough came in 2020, when LIGO and Virgo detected the event GW190521, the merger of two black holes producing a remnant of about 142 solar masses. This was the first direct evidence of an intermediate mass black hole. It was as if a mythological creature had stepped out of legend into reality. Philosophically, intermediate black holes speak to our yearning for continuity. Just as paleontologists search for transitional fossils between species, astronomers seek transitional objects between the stellar and the supermassive. Their existence suggests that the universe does not leap abruptly from one extreme to another, but passes through stages, weaving a seamless tapestry. The human story here is one of persistence. For decades, scientists scoured the skies, watching clusters, analyzing subtle shifts in starlight, building ever more sensitive detectors. Imagine the patience required to wait for a ripple in space-time, for two black holes to collide billions of light-years away, so that a fleeting signal might confirm a long-held suspicion. This is science at its most human, slow, patient, stubborn. Culturally, intermediate black holes remind us that darkness has shades. Not all black holes are the same. Some are infants, some are giants, some are adolescents caught in between. Even in the cosmic void, there is diversity and nuance. And so, the search continues. Each new observation tightens the net, suggesting that intermediate black holes may hide in star clusters, dwarf galaxies, or the remnants of primordial times. Perhaps they are rare, or perhaps we have simply not looked in the right way. But their discovery is more than a matter of cataloging. It is about completing the picture of how structure forms in the universe. In the end, intermediate black holes may prove to be the stepping stones to the supermassive giants. Or perhaps they will surprise us, revealing an entirely new path of cosmic evolution. Either way, they remind us that the universe still holds mysteries, and that the missing pieces may yet lie hidden in the dark. When we think of black holes, we usually imagine the corpses of stars or the giants at galactic centers. But some scientists believe there could be an even older population, black holes born not from stars, but from the earliest moments of the universe itself. These are the primordial black holes, children of the Big Bang. The idea first arose in the 1970s. Physicists realized that in the first fractions of a second after the Big Bang, the universe was an unimaginably hot, dense soup, full of violent fluctuations. In certain regions, the density could have been high enough for gravity to overwhelm all other forces, collapsing matter directly into black holes. Unlike stellar or supermassive black holes, primordial black holes could span an extraordinary range of masses. Some might be as small as asteroids or mountains, with event horizons measured in centimeters. Others could rival thousands of suns. This makes them unique testbeds for physics, bridging the gap between the micro and the cosmic. Why do they matter? For one, primordial black holes could help explain the mysterious dark matter that makes up about 27% of the universe. Unlike ordinary matter, dark matter does not emit or absorb light, but reveals itself through gravity. Could some of it be hidden in the form of ancient black holes drifting invisibly through galaxies? Scientists have searched for signs. If a primordial black hole passes in front of a distant star, its gravity might bend the light, producing a brief magnification, an effect called microlensing. Large surveys like MACHO, EROS, and OGLE have scanned millions of stars for such flickers, placing limits on how common these objects can be. Another approach is to look for gravitational waves from the mergers of low-mass black holes, which could point to primordial origins. Philosophically, primordial black holes are fascinating because they are fossils of the universe's infancy. If they exist, they are time capsules, preserving information about conditions we can never recreate in laboratories. To hold one in theory is to hold the memory of the cosmos itself, imprinted with the birthmarks of creation. Culturally, the idea has inspired both wonder and fear. In science fiction, tiny black holes are imagined as weapons or power sources. In reality, if a primordial black hole with asteroid mass passed through our solar system, it could cause chaos. Yet the very fact that we can even speculate about them speaks to how far our imagination reaches. Critics point out that primordial black holes cannot make up all of dark matter. Observational constraints rule out large populations across many mass ranges. Still, narrow windows remain open. Perhaps the universe does contain these ancient wanderers, but only rarely, hiding in the shadows between stars. The search continues, and with it, the questions. If primordial black holes exist, they could explain not just dark matter, but also the seeds of galaxies, the origins of structure, and even aspects of cosmic inflation. If they do not, then their absence is itself a clue, guiding us toward other solutions. Either way, primordial black holes expand our imagination. They suggest that black holes need not be the graves of stars. They can also be the first children of the universe, born not of death, but of birth. And if we ever confirm their existence, it will change not only astrophysics, but our sense of cosmic history itself. To understand black holes, we must look at their anatomy, though look is a strange word here, for we cannot see them directly. And yet, physics provides us with a remarkable mental map. At the core, a singularity, a place where density and curvature of space-time go to infinity. Surrounding it, the event horizon, the ultimate boundary of no return. And outside of that, strange regions where time and space themselves trade roles. Let us begin with the event horizon. It is not a physical surface, but a threshold. Cross it, and no signal, not even light, can escape. For an outside observer, objects falling toward the horizon appear to slow down, approaching it asymptotically, never quite crossing. For the falling object itself, however, the crossing happens in finite time. From that point on, the path to the center is inevitable, as if gravity itself has rewritten the rules of destiny. At the center lies the singularity, predicted by Einstein's equations, a place where the known laws of physics break down, where density is infinite and space-time curves beyond measure. For many physicists, the singularity is less a real object than a signpost. Our theories are incomplete here, and a deeper quantum theory of gravity is required. Between these two lies the strange interior where mathematics suggests that space and time exchange their roles. Moving toward the center is not a choice. It becomes as inexorable as moving forward in time. A black hole is not just an object, then, but a reshaping of reality itself. Philosophically, the event horizon is a powerful metaphor. It is the edge of knowledge. Beyond it lies the unknown, forever inaccessible. We may speculate, build models, argue in seminars, but no experiment can bring us data from within. Black holes, in this sense, remind us of the humility required in science, that there will always be horizons we cannot cross. And yet, scientists push forward. Stephen Hawking showed that black holes radiate, challenging the idea of the horizon as an eternal prison. Leonard Susskind and Juan Maldacena developed the holographic principle, suggesting that information falling into a black hole might be encoded on the horizon itself, like pixels on a cosmic screen. Others propose that the singularity may not be infinite after all, but replaced by some quantum structure, a remnant, a bounce, a new state of matter. The history of these ideas is rich with intellectual drama. Roger Penrose proved that singularities are not artifacts of mathematics, but inevitable in collapsing stars. For this, he received the Nobel Prize. Hawking wrestled with paradoxes, even wagering and later conceding bets about the fate of information. The debates themselves became legendary, showing how science advances not just through data, but through passionate argument. Culturally, the image of the event horizon has seeped into our imagination. It appears in films, novels, and music as the symbol of the ultimate boundary, the point of no return. To say, we are crossing the event horizon, is to say we are entering the unknown, with no way back. The singularity, meanwhile, is the archetype of mystery itself, a blank center, a place where comprehension collapses. So what do black holes teach us here? That reality has edges, that knowledge has boundaries, that there are places where our tools break, but also that these very boundaries are invitations. To confront a singularity is to admit we do not yet have the final word on nature. To imagine the horizon is to imagine new physics waiting just beyond. In the end, the anatomy of black holes is not just an astrophysical curiosity, it is a lesson in humility and ambition. They whisper to us, there is more to learn, more to discover, more to dream. And if the darkest places in the universe can still inspire wonder, then perhaps nothing is beyond the reach of human thought. Black holes are often imagined as silent devourers, swallowing everything in their path. Yet paradoxically, they are also among the brightest sources in the universe. Their feeding habits, through accretion disks, and their spectacular outbursts, through relativistic jets, make them cosmic lighthouses, illuminating vast stretches of space. Accretion begins when matter, gas, dust, even whole stars, ventures too close to a black hole. Instead of plunging straight in, the material swirls into a disk, heated by friction to millions of degrees. This accretion disk radiates intensely, often in X-rays, sometimes outshining the entire galaxy around it. To look at such a system is to witness energy conversion at its most extreme, gravity turned into light. Quasars, powered by supermassive black holes, are the champions of this process. Some are visible across billions of light years, shining when the universe was young. They are windows into cosmic history, allowing us to glimpse how galaxies and black holes grew together. But disks are only half the story. Many black holes launch jets, narrow beams of plasma shooting out at nearly the speed of light. The galaxy M87 hosts one of the most famous, a jet stretching thousands of light years. How are these jets formed? The details remain mysterious, but magnetic fields twisted by the black hole's rotation seem to play a key role channeling energy outward in colossal streams. Here lies a philosophical paradox. The very objects that trap light also give rise to phenomena that blaze brighter than anything else in the universe. Darkness and light are not opposites here. They are partners. The black hole is not just a void, but an engine. The human story of these discoveries stretches back a century. In 1918, Heber Curtis noticed a strange ray in the galaxy M87, the first recorded sight of a jet. Decades later, with radio telescopes and space observatories, scientists mapped jets across the sky. In 2019, when the Event Horizon Telescope revealed the shadow of M87's black hole, the jet was there too, a reminder of how history and discovery intertwine. Practically, jets and accretion shape the cosmos. They regulate star formation, heat intergalactic gas, and sculpt galaxies. Without them, the universe would be unrecognizable. Black holes, once thought to be destroyers, turn out to be regulators and creators, cosmic thermostats balancing the flow of matter and energy. Philosophically, this duality speaks to a deeper truth. Nature resists simple labels of good or evil, light or dark. Black holes embody both extremes, devourers and illuminators, graves and engines. Perhaps that is why they fascinate us. They mirror the complexity of life itself. And so, accretion and jets remind us that even in the darkest corners of the universe, light can emerge. Even the most destructive forces can fuel creation. Black holes, in this sense, are not just objects of fear, but symbols of transformation. Proof that out of the void can come brilliance, out of collapse can come radiance. When we picture a black hole, we might imagine a featureless sphere, distinguished only by its mass. But in reality, black holes can also spin, and this rotation is one of their most fascinating features. The spin of a black hole is not a detail. It is central to its identity, shaping the space-time around it, fueling jets, and storing the memory of cosmic events. A rotating black hole is described by the Kerr solution to Einstein's equations, discovered by Roy Kerr in 1963. Unlike a non-rotating Schwarzschild black hole, a Kerr black hole drags space-time around with it. This region of forced rotation is called the ergosphere. Inside the ergosphere, nothing can remain still. Even light must swirl along. Here, the fabric of reality itself is pulled into a cosmic whirlpool. The ergosphere is not just strange, it offers possibilities. In 1969, Roger Penrose proposed that energy could be extracted from a rotating black hole. If an object falls into the ergosphere and splits, one fragment might fall into the black hole while the other escapes with more energy than it had before. This Penrose process hinted that black holes could power the immense energies observed in quasars and jets. Later, the Blandford-Zanayak mechanism extended the idea, showing how magnetic fields and spin might combine to launch jets of plasma across galaxies. Spin also influences the horizon itself. A maximally rotating black hole can shrink its event horizon, exposing regions closer to the singularity. It affects the temperature of Hawking radiation, the dynamics of accretion disks, even the lifetime of the hole. In a sense, the spin encodes the history of how the black hole formed, whether it grew slowly from feeding or violently through mergers. Philosophically, the idea of rotating darkness is powerful. We think of void as stillness, of nothingness as calm. Yet here, even the absence is in motion, dragging the universe with it. It is a reminder that nothing in nature is static. Even the deepest silence has a hidden rhythm. Observationally, Spin is hard to measure, but not impossible. By studying the X-ray spectra of accretion disks or the shape of jets, astronomers can infer rotation rates. Some black holes, we now know, spin nearly as fast as the laws of physics allow. They are cosmic tops, whirling space-time at the edge of possibility. The human story of spin is tied to theory and daring imagination. Roy Kerr's solution was once a mathematical curiosity, but today it underpins our models of real objects. Penrose's insight about energy extraction anticipated entire fields of astrophysics, and modern astronomers, with their telescopes and detectors, turn these abstractions into empirical knowledge. Culturally, the spinning black hole resonates with archetypes of whirlpools, vortices, and maelstroms. Ancient myths spoke of cosmic eddies swallowing ships and worlds. Today, physics shows us that the cosmos itself contains such vortices, not as metaphor, but as fact. So what does spin teach us? That black holes are not mere sinks. They are engines, dynamos, sculptors of galaxies. Their rotation is a memory of their birth, a driver of their power, and perhaps a clue to the deeper laws of quantum gravity. To contemplate a spinning black hole is to glimpse the universe in motion at its most extreme. Among the most awe-inspiring events in the cosmos are the mergers of black holes. Imagine two invisible giants locked in a gravitational dance, spiraling closer and closer until they collide. In that instant, they release more energy than all the stars in the observable universe combined, not in light, but in ripples through the fabric of space-time itself, gravitational waves. Einstein predicted these waves in 1916, but for a century they remained theoretical. The distortions they cause are minuscule, stretching and squeezing space by less than the width of a proton. To detect them would require technology of extraordinary precision. Many thought it impossible. But in 2015, the impossible happened. On September 14, 2015, the LIGO detectors in the United States recorded the signal GW150914. It was the death cry of two black holes, each about 30 solar masses, merging into one. 3 solar masses worth of energy was radiated away as gravitational waves in a fraction of a second. Humanity had, for the first time, heard the universe. That discovery opened a new era: gravitational wave astronomy. Since then, dozens of events have been detected, from mergers of stellar black holes to the collisions of neutron stars. Each signal is like a drumbeat from the cosmos, carrying information about masses, spins, distances, even the nature of gravity itself. Philosophically, these detections changed our relationship with the universe. For millennia, we knew the cosmos only through light, the stars, the galaxies, the electromagnetic spectrum. Now we listen as well. The universe is not only something to see, but something to hear. This duality of sight and sound deepens our sense of connection to the cosmos. The energy of these mergers defies comprehension. In less than a second, they outshine the combined power of all stars. To reflect on this is to feel small, but also inspired. For even though we are fragile creatures on a small planet, we built instruments sensitive enough to register a tremor in space-time from billions of light-years away. The human story behind LIGO and Virgo is as inspiring as the discoveries. Ry Weiss, Kip Thorne, and Barry Barish dedicated decades to building the detectors, facing skepticism and setbacks. Their perseverance, along with the work of thousands of scientists and engineers, was rewarded with the Nobel Prize in 2017. It was not just a triumph of physics, but of collaboration, imagination, and determination. Culturally, gravitational waves captured the public imagination. Newspapers wrote of hearing the universe. Musicians turned the signals into melodies. Artists painted the invisible collisions. Science had once again crossed into art, and the boundary between them blurred. And so, black hole mergers are not only astrophysical events, they are symbols. They remind us that the darkest objects can send out the brightest insights, that silence can give birth to sound. Each ripple carries with it not just data, but meaning. To listen to gravitational waves is to listen to the heartbeat of creation itself. For a long time, black holes were thought to be eternal prisons, swallowing everything and never letting anything escape. But in the 1970s, Stephen Hawking made a discovery that changed our understanding forever. Black holes are not completely black. They radiate, and eventually, they evaporate. The key lies in quantum mechanics. In the vacuum of space, pairs of virtual particles constantly pop in and out of existence. Normally, they annihilate each other in a flash. But near the event horizon of a black hole, something extraordinary can happen. One particle falls in, while the other escapes. To an outside observer, it appears as if the black hole itself is emitting radiation. This Hawking radiation is incredibly weak for large black holes. For a black hole with the mass of the Sun, it would be utterly undetectable. But for small black holes, perhaps primordial ones, it could be significant. Over vast timescales, this radiation causes the black hole to lose mass, shrink, and eventually vanish in a final burst of energy. Philosophically, this was revolutionary. Black holes, once thought eternal, became mortal. They obey the laws of thermodynamics with entropy and temperature. The horizon is not just a boundary of no return, but also a surface that glows, however faintly. The deepest darkness has a flicker of light. Yet Hawking's discovery also gave rise to one of the greatest puzzles in physics, the information paradox. If black holes evaporate completely, what happens to the information about what fell in? Quantum mechanics insists that information cannot be destroyed, but if a black hole vanishes, it seems that information is lost. This paradox has haunted physics for decades, driving debates, conferences, and new theories. Some suggest that information is encoded on the event horizon itself, like pixels on a cosmic hologram. Others imagine that black holes leave behind remnants, tiny leftovers containing all the data. Still others propose exotic solutions involving wormholes or new dimensions. None of these ideas are proven, but all testify to the richness of the problem. The human story here is as dramatic as the science. Hawking himself initially resisted the idea that black holes could radiate, but his calculations forced him to accept it, even though it overturned long-standing beliefs. Later, he made and lost bets with colleagues about the fate of information, showing his willingness to embrace uncertainty. His courage in following the math where it led, despite his own doubts, made him a scientific icon. Culturally, Hawking radiation has become a symbol of paradox, appearing in films, novels, and popular science. It transformed black holes from mere destroyers into enigmas, inviting speculation and wonder. The idea that even the darkest voids glow with faint whispers of quantum light captures the imagination. So, what do we learn from Hawking radiation? That nothing in the universe is truly eternal. That even the most terrifying objects are subject to change. That death, even for black holes, is part of the cosmic cycle. And perhaps most profoundly, that mystery endures. The evaporation of black holes is not an end to questions, but the beginning of new ones. To contemplate a black hole evaporating is to contemplate impermanence at the grandest scale. It is to realize that the universe itself is dynamic, restless, unfinished, and in that impermanence, perhaps, lies its beauty. Black holes are not only astrophysical objects. They are natural laboratories where the two great pillars of modern physics, general relativity and quantum mechanics, collide. Each works perfectly in its own domain, relativity for the cosmic, quantum theory for the microscopic. But near the singularity of a black hole, both must apply, and there they clash. General relativity describes gravity as the curvature of space-time. Quantum mechanics describes the uncertainty and discreteness of particles and fields. Put them together, and infinities erupt. Singularities appear. Laws seem to break down. Black holes expose the cracks in our understanding, pointing toward a deeper, unified theory. Quantum gravity. One proposal is loop quantum gravity, which suggests that space-time itself is granular, woven from tiny loops. In this view, singularities are resolved. The infinite densities predicted by relativity are replaced by finite structures. Another contender is string theory, in which black holes are described as special states of vibrating strings and higher dimensional membranes. Their entropy, in this picture, can be counted by the microstates of strings, matching Hawking's thermodynamic predictions. Perhaps the most influential idea is the holographic principle, developed by Gerard T. Hooft and Leonard Susskind, and expanded by Juan Maldacena in the ADS/CFT correspondence. It proposes that all the information inside a volume can be described by data on its boundary. Applied to black holes, it suggests that information about everything that falls in is encoded on the horizon. This radical idea not only addresses the information paradox, but hints that the universe itself may be holographic. Philosophically, these theories are breathtaking. They suggest that reality may not be what it seems. Space could be emergent, time could be an approximation, and the world of experience could be a projection from deeper laws. Black holes, then, are not just endpoints of matter, but gateways to rethinking existence itself. The debates around these ideas have been legendary. Stephen Hawking and Leonard Susskind sparred for decades over whether information is lost in black holes. In the end, Susskind's perspective, supported by holography, won the consensus. But the discussions themselves fueled progress, showing how science thrives on passionate disagreement. Observations also play a role. The study of black hole thermodynamics, gravitational waves, and accretion flows all provide data that can test these theories. Though quantum gravity remains beyond direct reach, black holes bring it tantalizingly close. The human story here is about audacity. The willingness of physicists to challenge their own foundations, to imagine that space and time are not fundamental, to follow mathematics into realms stranger than fiction. Figures like Maldacena, Penrose, and Susskind are not only scientists, but explorers, mapping the borders of knowledge. Culturally, the image of black holes as laboratories resonates with our fascination with the ultimate experiment. In literature and film, they become test sites for time travel, wormholes, or gateways to parallel universes. In reality, they are experiments conducted by nature itself, at scales and energies no human machine could reach. So, what do black holes teach us as laboratories? That limits are opportunities, that contradictions are invitations, that the clash of theories is the birth of new ones, and that the deepest mysteries of the cosmos are not obstacles but doors, waiting to be opened by imagination and courage. Black holes exist not only in the equations of physics or the data of telescopes. They live in our imagination, our stories, our symbols. Long before science proved their reality, myths told of cosmic voids, devouring beasts, and bottomless abysses. In the modern age, black holes have become cultural icons, metaphors for death and rebirth, ignorance and knowledge, fear and wonder. In ancient myths, we find images that resonate uncannily with black holes. The Norse spoke of Ginnungagap, a yawning void between worlds. Hindu cosmology tells of Vishnu sleeping on the cosmic ocean, out of which the universe arises and into which it dissolves. Many traditions describe monstrous mouths devouring the sun or stars. Today, science tells us of horizons and singularities, but the archetype remains, the devouring darkness. In literature, black holes are fertile ground. In science fiction, they are portals to other universes, engines of time travel, or ultimate weapons. In Stephen King's novels, they appear as metaphors for destiny's pull. In Christopher Nolan's film Interstellar, the black hole Gargantua became a cinematic character, its image crafted with scientific accuracy by Kip Thorne. That image was so precise it generated new research papers. Here, art and science merged. In art and music, black holes inspire attempts to express the inexpressible. Painters depict spirals and vortices. Composers write symphonies evoking cosmic gravity. Even in popular music, the phrase black hole conjures mystery and emotion. The scientific concept has crossed into the realm of metaphor, where it gains new life. Philosophically, black holes stand for the boundary of knowledge. The event horizon is not only a physical edge, but a metaphorical one, the point beyond which we cannot know. Immanuel Kant spoke of the thing in itself, forever beyond our perception. In black holes, this idea takes a cosmic form. They remind us that mystery is not a flaw in knowledge, but an inherent feature of existence. At the same time, they symbolize inspiration. They are not only ends, but beginnings. In stories, heroes who venture near black holes often do so not to die, but to discover. They represent risk, transformation, and the promise of deeper truth. Thus, the black hole becomes a symbol of hope as much as fear. The human stories of scientists add to this cultural tapestry. Stephen Hawking became a cultural icon not just for his science, but for his image, his voice speaking of black holes through a computer as if channeling the universe itself. Roger Penrose's mathematical insights, Kip Thorne's cinematic collaborations, Juan Maldacana's theoretical elegance, each has made black holes not just objects of study but of wonder. Culturally, black holes are mirrors. We project into them our anxieties, our desires, our philosophies. They are symbols of annihilation and of transcendence, of the void and of creativity. They remind us that the universe is larger than our comprehension, and that this very fact is what drives us to create stories, art, and science. So black holes are not only astrophysical realities, but cultural phenomena. They stand alongside myths of creation and apocalypse, inspiring art, literature, music, and philosophy. They are symbols of what it means to be human in a vast and mysterious cosmos. To contemplate them is to contemplate ourselves, finite beings gazing into infinity, daring to imagine the unimaginable. As our journey through black holes nears its end, we must pause and reflect on their place not only in science, but in the human imagination. Black holes are more than astrophysical objects. They are symbols, metaphors, canvases upon which we project our fears, our hopes, our questions about existence. In contemplating them, we contemplate ourselves. In popular imagination, black holes often stand for the ultimate unknown. They are the abyss, the edge of the map where certainty ends. To say something is a black hole is to say it consumes resources, time, or attention without return. This metaphor reveals a truth. We fear what we cannot control, what we cannot see beyond. But black holes also inspire wonder. The image of an event horizon glowing with an accretion disk suggests not just destruction, but beauty born from extremes. To artists, they are the sublime in its purest form, terrifying yet magnificent. To philosophers, they are puzzles about knowledge and reality. To storytellers, they are portals, thresholds, challenges. Every discipline finds in them a mirror of its own concerns. There is something deeply human about our fascination with boundaries. We build ships to cross oceans, rockets to pierce the sky, telescopes to peer at galaxies. The event horizon is the cosmic boundary par excellence. We cannot cross it, yet we are drawn to its edge in thought and imagination. To dream about what lies beyond is to express the very essence of curiosity. The stories of scientists illustrate this imaginative drive. When John Wheeler coined the term black hole, he gave not only a name but a metaphor, a handle for the public mind. When Kip Thorne collaborated with filmmakers to depict Gargantua, he brought the equations of relativity into the language of cinema. When Stephen Hawking spoke of information paradoxes, he invited the world to ponder mysteries usually confined to chalkboards. Each act was not just science, but storytelling. Culturally, black holes have become part of our collective mythos. Just as ancient peoples told tales of underworlds and heavens, we tell tales of horizons and singularities. The difference is that today our myths are grounded in data, telescopes, and mathematics. Yet they serve the same role: to give shape to the unknown, to turn mystery into meaning. Philosophically, black holes embody paradox. They are both nothing and something, void and mass, end and beginning. They challenge binary thinking, reminding us that reality is often both and, not either or. They invite humility, reminding us that our knowledge is limited. But they also inspire courage, showing us that limits are invitations to go further. To imagine black holes, then, is to engage in an act of self-discovery. We are finite beings dreaming of infinity. We are fragile creatures daring to calculate the physics of singularities. We are storytellers who turn equations into metaphors, data into meaning. The black hole is a cosmic mirror, and in it, we see ourselves. And so, black holes inspire not just science but art, not just equations but poetry. They are symbols of despair and of hope, of silence and of song. In their darkness, we find light. In their finality, we find possibility. In their mystery, we find meaning. This, perhaps, is their greatest gift. Not only to challenge our physics, but to challenge our imagination. To remind us that the universe is bigger than our fears, deeper than our doubts, richer than our stories, and that in gazing at the abyss, we do not lose ourselves. We find ourselves. Our journey together now comes to its end, my dear listeners. We have traveled through the life cycle of black holes, their births and the deaths of stars, their growth into supermassive giants, their mysterious middle forms, their accretion disks and jets, their spins and mergers, their paradoxes and their radiation, their roles in culture and imagination. And now, in this final chapter, let us step back and ask, what do black holes mean to us? Black holes are not just astrophysical entities. They are symbols of the human spirit's greatest qualities: curiosity, persistence, imagination. Once, they were dismissed as mathematical oddities, absurd consequences of Einstein's equations. Even Einstein himself doubted their reality, and yet, through observation, theory, and daring, we proved they exist. More than that, we have imaged their shadows, measured their tremors, and traced their influence across billions of light years. Philosophically, black holes remind us that the universe is stranger than we can imagine. They show that space and time can bend, twist, even vanish. They challenge our deepest assumptions about causality, information, and reality itself. They whisper that our current theories are incomplete, that deeper truths await. They are cosmic invitations, daring us to seek what lies beyond the horizon of our knowledge. But black holes also mirror our own condition. We too live within horizons, the limits of perception, the boundaries of life. We too face singularities, moments of crisis, collapse, transformation. And like black holes, we contain mysteries within us, depths that cannot be fully measured or explained. To study them is, in a sense, to study ourselves. The human stories of black hole science are lessons in resilience. Roger Penrose, proving that singularities are inevitable. Stephen Hawking, confronting paradoxes with courage. Andrea Ghez, patiently watching stars circle an invisible center. Kip Thorne, bridging physics and film. Each of them, in their own way, gazed into the abyss and did not turn away. Instead, they brought back knowledge, beauty, and inspiration. Culturally, black holes have moved from objects of terror to sources of wonder. They are no longer only destroyers. They are creators, regulators, even muses. They shape galaxies, inspire art, and provoke philosophy. They stand alongside myths of creation and apocalypse, but with a difference. They are real, and we can measure them. They unite myth and science in a single awe-inspiring whole. Why, then, are we so drawn to them? Perhaps because they embody the paradox of existence itself. Endings that are beginnings, darkness that gives rise to light, silence that speaks. They show us that the universe is not static but dynamic, not simple but profound. And in their enormity, they remind us both of our smallness and our greatness. Small because we are tiny compared to them, great because we can comprehend them. The most inspiring lesson of black holes is this: even the darkest places can shine. From the edge of the event horizon, accretion disks blaze. From mergers, gravitational waves sing. From evaporation, Hawking radiation glimmers. Black holes transform collapse into creation, silence into sound, void into meaning. They are paradox made manifest. And in that paradox lies beauty. So as we close this journey, let us carry with us the message of black holes. That mystery is not to be feared, but embraced. That boundaries are not walls, but doors. That the unknown is not emptiness, but possibility. Black holes are not just out there in the cosmos. They are within us, in our questions, our dreams, our courage. Thank you for traveling this path with me. May black holes continue to inspire us, not only to explore the universe, but to explore ourselves. For in the end, the true horizon is not out there in the stars, but in the limitless expanse of the human spirit.